14 kilometers of water, approximately 8.7 miles, is all that separates Europe from Africa. It sounds like if humans could tunnel underwater and build bridges dozens of miles long, this would be the easiest place to do it. But in reality, it's one of the most difficult places to construct on the planet. Here, two oceans collide, creating powerful underwater eddies capable of uprooting concrete pillars weighing thousands of tons. To build this bridge, humans would have to conquer depths of nearly 3,000 feet, 3 times the height of the Eiffel Tower. And that's not all. Extremely strong ocean currents constantly exert immense pressure on the entire structure. Today we'll analyze this insane project and explore why even the world's best engineers haven't been able to cross those 8.7 miles of water. By the end of the video, you'll know what discovery at the bottom of the strait made building this bridge almost physically impossible. Imagine standing on the Spanish coast in Tarifa and seeing the white houses of Tangier in Morocco. Everything looks so close, almost within reach. But that very illusion has deceived generations of construction engineers. While you gaze at the horizon, hundreds of truck drivers at the port of Algeciras are helplessly banging on their steering wheels, having waited for the ferry for the second consecutive day. The logistics system between the two continents is now like a broken clock. Trucks carrying vegetables from Africa and electronics from Europe are stuck 8.7 miles across the water, turning a short distance into a grueling journey. Every hour of delay means thousands of gallons of fuel burned and millions of dollars lost. A bridge here could become a gold mine, transforming all this chaos into a continuous transport chain operating at speeds of around 75 miles per hour. The race to conquer Gibraltar began in the 15th century, when the first engineers tried to convince the kings that the project was entirely feasible. By the mid-20th century, the Spanish and Moroccan governments began to turn words into action. They formed research teams, dispatched survey ships, and began drilling the first exploratory boreholes. Future routes appeared on maps, and politicians prepared to announce the official commencement of work. But as soon as the first borehole touched the seabed, the excitement quickly turned into anxiety. The equipment kept malfunctioning. The data obtained exceeded all existing construction textbooks. Do you think the biggest problem was money? In reality, investors have long been ready to sign checks for any amount. But for hundreds of years, no architect dared to sign the final design. Today, the situation in the strait is more tense than ever. While government agencies in Madrid and Rabat continue to study the bridge project, a real battle with nature is raging on the water. Ferries are struggling against the rough waves to transport even a small fraction of the enormous volume of goods piling up on both banks. Just one ship's malfunction can instantly paralyze the entire region's transportation system. Giant trucks are forced to turn around and take thousands of miles of detours across the sea just to avoid getting stuck in this bottleneck. But why, when we've built bridges across large bays and dug underwater tunnels, are we still powerless here? Look around. ABC. On the surface, everything seems peaceful, but beneath each ship lies a force capable of crushing any steel pillar. You'll soon understand what has made even the world's best engineers retreat in fear before this coastline. To understand the scale of the problem, imagine Gibraltar is not just an ordinary strait, but a constant collision point between two oceanic giants. Here, the cold waters of the Atlantic meet the saltier, denser waters of the Mediterranean. Due to differences in density, they cannot simply mix together. The heavier, saltier water from the Mediterranean sinks to the bottom and flows into the Atlantic, while the lighter water from the Atlantic flows strongly above in the opposite direction. As a result, at the same location, water moves simultaneously in two opposite directions. The upper layer of water hundreds of feet thick rushes in one direction, while the lower layer flows in the opposite direction. This phenomenon creates tremendous pressure. Any standing pillar in this body of water is at risk of being crushed. If you lower a long steel column into the water, the top part will be pulled strongly eastward, while the bottom part will be pulled westward. Imagine a massive structure constantly being torn apart or twisted in two different directions every second by two invisible hands. The speed of these currents reaches approximately 13 feet per second, an enormous number for water. The immense volume of water exerts such pressure on the foundation piles that ordinary concrete would begin to crack within months. The subsurface waves are so powerful, they can toss even 1,000-ton submarines up and down dozens of feet, disorienting them. But the most terrifying detail lies even deeper and is completely invisible from the surface. In Gibraltar, internal waves exist forming at the boundary between two layers of water with different densities. The surface of the sea may be perfectly calm, but at depths of nearly 1,000 feet, water mountains, over 330 feet high, are moving. These giant underwater waves carry tremendous energy from the ocean floor. When they strike bridge pillars, the impact force is equivalent to the collision of a 1,000-ton train traveling at full speed. These waves are formed by the rugged seabed topography, turning the entire space between the two shores into a constantly battered area. The situation is further complicated by the fact that these phenomena are almost unpredictable. The research equipment that scientists install to measure them frequently disappears or is completely damaged upon retrieval. In many areas of the seabed, deep trenches created by extremely powerful currents have been discovered so strong they can sweep massive boulders as if they were mere pebbles. Nowhere else on the planet do bridge engineers face such a combination of immense depth and turbulent currents as here. Add in the constant whirlpools, and it's easy to understand why any standard bridge pier would be a target for this giant hydraulic hammer. Many believe that simply creating super strong pile foundations would suffice. But in Gibraltar, there are no still waters. Even at the seabed, the water is constantly moving, not for a single second. Engineers calculated that the total pressure exerted on the bridge structure would be dozens of times greater than the load-bearing capacity of even the world's strongest materials. Every design that looked perfect on paper was deemed unfeasible after initial tests in a simulation tank. We usually think of water as a soft, yielding medium, but here it behaved like a giant, ruthless press. However, it was later realized that these currents were only the beginning of the problem. The real impasse arose when engineers studied the terrain at the bottom of the strait. It turned out that the Gibraltar seabed was not at all a stable, flat surface suitable for foundation construction. Imagine a vast underwater canyon with sheer cliffs and jagged rocks. At its narrowest point, the depth reaches nearly 3,000 feet. To put it simply, imagine 3 Eiffel Towers stacked on top of each other, completely submerged in the abyss. Even the shallowest area, the Camarines Ridge, is nearly 1,000 feet deep. The biggest hurdle for engineers is installing the bridge piers. A conventional bridge requires massive concrete columns anchored securely to solid ground. But currently, no technology exists to secure a structure weighing tens of thousands of tons at depths of thousands of feet under such turbulent currents. But currently, no technology exists to secure a structure weighing tens of thousands of tons at depths of thousands of feet under such turbulent currents. It's not simply a matter of lowering the columns to the seabed, they must be placed with absolute precision on the bedrock under immense water pressure. Just a 1-degree deviation could cause the entire pier to collapse under its own weight. How can foundations be built where even surveying robots struggle to maintain their position? The famous Akashi Kaikyo Bridge in Japan is often cited as an example. But compared to Gibraltar, the Japanese project is a mere walk in the park. The depth of the piers there is only about 200 feet less than 5 times the depth of the most favorable area in Gibraltar. The experience of Turkish or Danish engineers here is almost useless. It's like trying to build a skyscraper using the principles of assembling children's toys. The combination of vast distances and extreme depths renders all existing construction experience in the world obsolete. What almost killed the entire project was the geological structure of the seabed. Preliminary studies show that the seabed is covered by layers of material whose stability is highly debated. Building on that foundation is like placing a heavy cabinet on a mattress filled with sand. The bridge piers need to stand for decades, but the seabed in the Strait of Gibraltar constantly presents unpredictable challenges. Engineers face a series of natural traps, and just one of them would be enough to make construction impossible. Traditional methods are completely ineffective here. This forces scientists to come up with ideas that sound more like science fiction than practical engineering. But before even considering flying bridges, engineers face another threat. Are you ready to know why this project could collapse due to the very processes occurring deep within the Earth? When traditional concrete pillar designs were thrown into the trash, engineers began proposing ideas that would have been considered crazy 30 years ago. If it can't rely on the seabed, then why not have the bridge float on the water? One of the most discussed ideas is a floating bridge built on giant pontoons. Imagine floating structures the size of a house holding the road surface like a buoy on a fishing rod. At first glance, this seems like the perfect solution. No need to drill down to the nearly 3,000-foot deep seabed. But as soon as mathematicians began the calculations, the optimism quickly turned into new concerns. The problem came from an unexpected source. Gibraltar is one of the world's busiest shipping lanes. Every year, tens of thousands of giant oil tankers pass through this 8.7-mile stretch of water. A floating bridge would become an insurmountable obstacle for them. A single mistake by the captain or a malfunction in the engine of a ship weighing over 300,000 tons could turn the bridge into scrap metal in seconds. Furthermore, the pontoons had to be anchored to the seabed with steel cables as thick as an adult's body. In the environment of constantly turbulent water currents, these anchors would bear loads beyond their capacity to handle. Then another solution was proposed: a suspension bridge with a record-breaking span of over 3 miles. To keep that structure afloat, it would require pillars over 1,600 feet tall, much taller than many modern skyscrapers. But this time, the engineers hit the limits of the material itself. It turned out that the steel cables under the enormous load would begin to stretch and lose their strength simply because of their own weight. Humans had reached a point where metal was no longer reliable enough. If the cables were thicker, they would be so heavy that the entire bridge would collapse before the first car could cross. Then attention shifted to underwater tunnels. If you can't go above the water, then go below. This idea would solve the problem of storms and giant ships on the surface. A railway tunnel project under the strait was proposed. But Gibraltar is not the English Channel, where the seabed is mostly soft chalk and easy to excavate. Here, preliminary surveys show that the geological composition changes every 330 feet. Hundreds of millions of dollars worth of tunnel boring machines risk getting stuck in a mixed geological mass that no one can accurately predict. Every new solution encounters an insurmountable physical barrier. Humans create super-strong alloys, but Gibraltar is always one step ahead. And while the world's brightest minds are debating the thickness of the steel cable, the Earth beneath the strait is preparing a gift that all calculations fail to deliver. Have you ever considered what would happen if two giant continents were moving toward each other right where you planned to build a bridge? Just as engineers began to understand how to counteract ocean currents, nature delivered its biggest blow. It turns out the Strait of Gibraltar isn't just a crack in the earth, but a direct collision between two massive tectonic plates. Here, the African and Eurasian tectonic plates meet. The most terrifying thing is that they aren't stationary. Africa is slowly but continuously moving north, gradually encroaching on Europe. Imagine building a bridge nearly 9 miles long while the two ends are constantly being pressed together. This movement creates another danger: intense seismic activity. The Strait area is prone to earthquakes due to pressure buildup in the Earth's crust. Historically, it has witnessed catastrophic events that wiped out entire cities. If a traditional rigid bridge were built here, a single major earthquake would be enough to turn it into a pile of rubble. During an earthquake, the piers at both ends would move in different directions. Today, no technology exists that can create a structure both flexible enough to withstand strong vibrations and rigid enough to support thousands of tons of weight. But even if the earthquake problem were solved, another issue would arise right beneath the seabed. Detailed studies revealed that the seabed consisted primarily of soft, extremely hazardous sedimentary layers. In fact, it resembled a thick, sticky paste of clay and sand stretching thousands of feet deep. Placing bridge piers there would be like sticking an iron rod into a swamp. It would slowly sink. These layers of soil change properties under water pressure or even from very small vibrations. How could a permanent structure be built where the very foundation of the soil was unstable? Researchers attempted to find at least one area with truly solid rock, but the results were extremely disappointing. Almost the entire seabed of the construction site was covered by loose sediment accumulated over millions of years. This meant that to lay the foundation, one would have to penetrate this entire layer of material to reach solid bedrock at nearly inaccessible depths. Continuous currents also eroded beneath these soft layers of soil, creating dangerous voids. At Gibraltar, the land itself was the least reliable ally. Constant tectonic pressure was pushing the shores closer together. Earthquakes constantly threatened to destroy any structure, and the seabed refused to bear the load. Engineers were faced with the challenge of conquering their own planet, a planet that resisted any intervention. And just when everyone thought the list of difficulties was complete, the scientists conducted one final scan. What they discovered beneath the mud made the project almost physically impossible. Are you ready to hear about the discovery that put an end to humanity's greatest engineering dream? When engineers' last hope rested on finding a stable foundation, international research teams conducted a decisive geological scan. They used ultra-powerful sensors and drilling systems capable of operating at extreme depths. Everyone hoped to find solid bedrock beneath the mud. But the seismic analysis results shocked experts. Instead of a stable foundation, the equipment detected a massive layer of loose sediment characterized more by a thick, viscous paste than by actual ground. Drilling confirmed that the seabed of Gibraltar is covered by thousands of feet of unstable clay. Under immense water pressure and constant vibrations from tectonic plates, this mass of material exists in an extremely fragile state. Even a small external impact would immediately cause it to lose its stability and behave like a liquid. This phenomenon renders pile driving pointless. Any heavy pile would sink under its own weight without sufficient resistance. But why are there so many layers of soft soil at Gibraltar? The answer lies in the distant past. About 6 million years ago, the Mediterranean Sea almost completely dried up. When the natural dam at Gibraltar collapsed, the Atlantic Ocean poured in with tremendous force. That ancient mega flood crushed rocks into fine dust, depositing it precisely in this narrowest area. The ancient catastrophe created a seabed structure that millions of years later has become an insurmountable barrier to modern technology. Today, the scientific conclusion is clear. A traditional bridge cannot be built here. Humans can create super durable materials, but they cannot change the nature of the seabed, which is simply incapable of providing a foundation. Any drastic intervention in this system risks causing large-scale underwater landslides. The dream of connecting two continents remains a bold idea, crushed by the planet's geological realities. Gibraltar remains a place where nature imposes its own rules, reminding humanity of its true limitations. If you enjoy stories about how nature challenges humanity's most ambitious projects, subscribe to the channel. Here we analyze the mysteries of the planet that have baffled the world's best scientists for decades.